Julianne Chambers, and today I will be discussing the analysis of free jet flow, lab number 2. The topics to be discussed in today's presentation are the purpose of the experiment, the introduction, the theory and all relevant information on the study, equipment and procedure followed in the experiment, the analysis of the data collected, discussion questions, and a conclusion. The purpose of this experiment is to analyze free jet flow through an orifice to determine the coefficient of contraction, the coefficient of velocity, and the coefficient of discharge as measured on the orifice through which the free jet was taken. This will be accomplished using two principles, Bernoulli's equation and the conservation of mass. A free jet is the result of a fluid stream through a flow meter. A flow meter is an orifice with a circular cross-sectional area which is fitted to a pipe or the face of a reservoir. The basic principle of this study is that a stream passing through the orifice will curve as it passes through the small flow area, where the fluid will increase in velocity and decrease in pressure as the stream shortens. The cross-sectional area of flow will decrease shortly after exiting the orifice due to the viscous effects of turbulent flow. This narrow window through which the stream passes is called the vena contracta, where, as shown in the following diagram, the flow narrows through the orifice and it narrows further before expanding. This vena contracta usually occurs half the diameter length away from the orifice surface. In this experiment, we'll measure the vena contracta, the velocity, and the flow rate to determine the coefficient of contraction, coefficient of velocity, and the coefficient of discharge. The coefficient of contraction is the ratio between the area of flow to the area of orifice. This is always less than 1 and typically ranges from 0.62 to 0.7. The coefficient of velocity is calculated by the ratio of measured velocity to theoretical velocity. It is also always less than 1 and is usually close to 1, ranging from just 0.96 to 0.99. And the coefficient of discharge is the result of multiplying Cc and Cv. This experiment will use two principles to understand and analyze the properties of the free jet flow, Bernoulli's and the conservation of mass. Bernoulli's equation is a commonly used equation in fluid mechanics and hydraulics, which analyzes the relationship between pressure, velocity, specific gravity, elevation head, and losses. Bernoulli's equation allows us to analyze these variables in different derived equations, which can be found in the analysis of data slides. The conservation of mass principle helps us determine flow rate by knowing the mass of fluid coming in must equal the mass of fluid coming out. The following equipment was used in this procedure: a tank reservoir with a 2x2 cross-sectional area and is at least 5 feet high, a 3/4 inch diameter orifice, a bin to collect water and a scale to measure the mass, a stopwatch, and a caliper, which is a sliding ruler that was used to measure the vena contracta. The following is the procedure used in exercise 1, which was to determine the coefficient of contraction, velocity, and discharge. The first step is to fill the tank with at least 50 inches of water. Second step is to open the orifice and adjust the inlet valve to obtain steady state conditions. That is, water in is equal to water coming out, and the height should remain at about 50 inches the entire time. We will then measure the X and Y values. X measurements will be taken on the pan below the free jet flow and can be recorded by sliding the wired frame until it comes in contact with the middle of the stream. The Y value is the measured distance from the orifice to the pan. We will then measure the vena contracta using the calipers. Step 5, we will use the bin and the scale and redirect the free jet into the bin on the scale to record the time it takes to fill the bin with 37 pounds of water. We will then change the inflow rate and maintain steady state conditions by about 5 inches, and we will repeat steps 3 through 6 for 6 sets of data by decreasing the head as stipulated in step 6. The following is the procedure used in exercise 2, which was used to take the time to empty the tank. First, we'll plug the orifice and increase the head in the tank to 55 inches. We will then unplug the orifice and record the time for the water level to drop until 30 inches in 5-inch increments. The following is the analysis of data in exercise 1. Table 1 shows us the recorded measurements taken during the lab, and Table 2 shows all the computed measurements from Table 1. We found in the following table that the coefficient of velocity ranges from 1.11 to 1.14. This is clearly wrong, as coefficient of velocity should never be above 1. We can have this due to human error, where we estimated that the actual velocity was much faster than it was. This was with difficulty redirecting the free jet stream in order to measure the flow rate. The calculated coefficient of contraction ranges from 0.25 to 1. These values remain below 1, which is what was expected. The following equations were used to analyze the data in exercise 1 in this order, and the following equations were all derived from Bernoulli's principle. The following graph shows the relationship between the coefficient of velocity, contraction, and discharge versus height as computed in the previous slide. As we can see, the coefficient of velocity does not vary much as compared to head. This is expected, as we know the coefficient of velocity theoretically has a very narrow range. The coefficient of contraction and the coefficient of discharge, however, had an inversely proportional relationship to height. The following graph shows the relationship between the two different ways that we computed the coefficient of discharge. The first way was by multiplying the actual calculated coefficient of contraction and velocity, and this coefficient of discharge is inversely proportional to head, which is expected because the coefficient of contraction varied greatly. The coefficient of discharge 2 that we measured was based off of flow rate, cross-sectional area, and height. And this one did not vary much. That is to be expected, as our actual flow rates that we measured also did not vary much, with difficulties with the tool and actually maintaining hugely different flow rates. Below is the relationship between flow rate and head, which is proportional. The following is the analysis of data from exercise 2, in which we calculated time. We calculated time and measured time. The theoretical time was calculated using the following equation, and the percent error was calculated comparing the two. The percent error for the theoretical time ranged from 3.15% to 10.46%. Following are discussion questions addressed in this lab. Number 1, what is the coefficient of contraction CC, and what is the typical range for CC? Our calculated CC values range from 0.25 to 1. CC typically ranges from 0.62 to 0.7. The reason for the difference in our data and the typical ranges are probably due to the difficulty using the caliper instrument. Number 2, what is the coefficient of discharge CD, and list the two different ways you are estimating CD. Below are the two equations used to calculate coefficient of discharge. The first way we used had a range from 0.28 to 1.14. This is to be expected, as the coefficient of contraction had a large range. The second way we calculated the coefficient of discharge was based off the actual measured flow rate, the cross-sectional area, and the height of water. These values barely had any range from 0.27 to 0.28. This is due to the difficulty of obtaining varying levels of flow rates. In conclusion, this experiment successfully allowed us to observe a free jet through an orifice and explain how to analyze the data using Bernoulli's principle and mass conservation. These principles allowed us to calculate the coefficient of velocity, the coefficient of contraction, and the coefficient of discharge, with success in measuring the last two and a little difficulties measuring the coefficient of velocity. Thank you.